these series of pictures and videos of the backwater laboratory that you would do in the Water Engineering 3 module, Cive 3415. I'm going to demonstrate the channel, the measurements, the measuring devices, the pump, etc. So you'll get a picture of everything in the lab and all the measurements taken. So this is the channel, or this is the upstream part of the channel, about 5 meters long. The channel is 16 meters in length, about 60 centimeters wide, and we'll get a depth of between 5 centimeters and 20 centimeters. Okay, we're going to just look at the different features of this channel now. To take measurements, you'd have to walk on this walkway and look inside the channel, and we'll get some videos of seeing that. So here's a bit longer shot of the channel looking upstream. There's that sluice gate that we just saw, and there's fluid flowing in it, so it's flowing down this way and going to flow out at the other end. So at this top upstream end there's a sluice gate, and at the downstream end there's a weir, and there's me adjusting the weir here. So you can see how the water is flowing that way, and we're going to take measurements of the depth and get the flow profile all along that channel, and get this at every meter along here. 17 readings, it's 16 meters long. At the upstream end there's the sluice gate forcing low depth and supercritical flow, and at the downstream end there's an adjustable weir lifting the level of the water, so you get a higher depth of water at the downstream end. The flow in the whole system is controlled by this pump. That sets a certain flow rate, but it's actually also adjusted by 2 valves. By changing these valves, if we can close this and close this valve, so the water goes from this pump along the pipes and eventually comes into the upstream end of the channel where it goes down here, and then it comes out at the end of the channel and eventually goes back into the pump. So it's a recirculating system. There's a flow meter on the system. It's actually electromagnetic, and it counts the flow, and there's a reading on it which we have to take note of. This isn't the reading from the lab, so you take note of the data in the Excel sheet, but do note that the units are in meters cubed per hour, and we always want units of flow in meters cubed per second, so you do need to adjust that. We're going to measure depths with these rather old-fashioned vernier scales. They've got a scale on this brass part here. We have to zero them, so we'll put a 0 when it's actually just touching the water surface, but we can get actual fine measurements to the millimeter by adjusting this here. So they are reasonably accurate for measuring down to the millimeter, and no more than that, but we'll see a bit later about accuracy of measuring water surfaces. When you're looking at a lab, you should always think about the health and safety, and if you do get into this lab, PPE rules say you must wear a hat, so you didn't get the opportunity to wear such a nice hat like that. So here's what we're trying to cause in this channel. We're trying to cause a hydraulic jump. Now here's the hydraulic jump. We've got slightly higher water here than we do down here. You can't actually see it in that picture, but we'll see it in a moment. So if that's the hydraulic jump we're trying to cause, and that's what we're trying to measure, and that's what we're trying to predict the position of. How do we cause that hydraulic jump? Because, well, I've said already, we've got an upstream sluice gate that gets the depth low. Now this is about 5 centimeters. You don't actually need to measure it for the lab. You need to measure the depth of the water, but that forces it down low. That's it flowing with some water in it. Actually goes a bit lower than 5 centimeters, so we get about 3 centimeters. And here's the flow in the channel. So that's going quite fast. That's the supercritical flow we had in the channel. Just to note, just upstream of that sluice gate, we've got a fairly constant level of water. You know that it's very near the top of the tank. So if you've read the lab instructions, this is what it was talking about being careful about this not overflowing, because it does overflow the tank and flood the laboratory quite regularly if you're not careful. The downstream end is an adjustable weir, so we can just raise this weir up and down to get a different height, change the height of the downstream end so it changes the height and position of the hydraulic jump. This is it with some water flowing over the end. There's another shot so we can see if the water's coming over the top here. We're looking underneath here, so that was it's flowing over there. We're just looking to see where it's coming through. And there it is again. It's good to see it in action. It's just right. So you see about 8 centimeters of water going over that weir. So we've got now the upstream end, which is a sluice, the downstream end, which is a weir. Here's a walkthrough of the whole channel in action. I'm walking down towards the hydraulic jump, walking past a couple of the vernier depth measuring gauges. There's the jump. And now we're going into subcritical flow. It's fairly fast at this point. It's getting deeper and deeper and it's slowing down. The surface is getting smoother. So we reach the very end that goes over the edge into the tank, and then we circulate through the tank. Okay. So what we're interested in is the hydraulic jump in the middle section, and the middle section has this perspex sides, so that we can see the hydraulic jump and look at it a bit closer. So here's the hydraulic jump in action. You'll see that it's actually moving very slightly downstream. This is because not reached a steady state yet, but we've just been adjusting the downstream move. At the point where it's all reached steady state, everything stops. Moving around, we've started to do the extra. Okay, so we're just going to look a little bit more in detail at the hydraulic jump. You'll see in this one we've got a shape that's like this, where I've talked about it in the lectures as though it's a straight across the channel, and theoretically it is, but there's some friction edge effects here that are causing this shape. So we need to take that into account when you're writing it up. If there's some errors, there's one for you to see. Let me just go and video and show how this looks running live. You can see downstream as well that it's also very rounded. With upstream it is smooth and super quick. It's highly turbulent there on this downstream side of the engine. So the second video here, showing something similar, slightly different angle. Hopefully you can just see it's highly turbulent front of the jump there. That's always going to be the case. There's a lot of energy lost in the jump. Remember, we didn't analyse this with the energy equation because we found that energy was this turbulent. Okay. Was thinking about sub and supercritical flow, and these pictures enable you to just realise what's happening. In supercritical flow, all the information, all the waves are flowing downstream. They're going back, they're going that way, so the flow is this way, and everything is going downstream. So you put something in the channel like this this measuring device, and it only affects everything downstream. In subcritical flow, we get little waves coming back up. They're also going downstream. So subcritical flow affects both upstream and downstream, and that's an important thing to realise. You've seen this in this lab already. When we've raised the weir, it's actually increased the depth further upstream. So subcritical flow affects both upstream and downstream. Supercritical flow only affects downstream. So you can do a test for sub or supercritical flow by sticking a stick in the flow like this, or indeed sticking your finger in the flow like I did, and this is in the supercritical flow and everything's going downstream like that. So I'll just have a look at a couple of pictures of videos of sub and supercritical flow. In the subcritical flow, you see some short waves going upstream. Supercritical flow, so it's not just about fast and slow for supercritical and subcritical. It's about the way that the information or the waves, the effect, which way is it going. So subcritical goes both upstream and downstream. Supercritical goes just downstream. So we just need to consider the measurement accuracy that we can get in this experiment, particularly in the very turbulent parts. So see these pointers are trying to touch the surface, but the surface is moving. So although we'll do our numerical methods down to accuracies of millimeters, we're not able to actually predict that or measure that very well in the lab. So I've just shown you these videos to show you the actual accuracy you can get, and then you can consider that when you're doing your write-up. We have to guess what was the height that we're measuring of that surface. So think about that in your accuracy discussion. Here's another video in just downstream of the jump, where it is highly turbulent. So sometimes that was very highly submerged, and sometimes it was above the surface. So the point we had there was estimated as the average. So again, another shot of a similar measurement at that point. Very difficult to take accurately. So what have you got to do with this lab? you have to produce a graph rather like this. Now it's explained more in the lab report, but I may just go over it slightly here. You're going to be plotting your measured data, or the measured data that is in the Excel file that you'll find in Minerva, and these red triangles, crosses, are the measured data. Then you will be doing an integration. Well, in fact, two integrations. You're going to start at the upstream point, the first measurement, right, and you're going to do an integration along to do that line. Then you're going to, so that's the supercritical integration. Then you're going to do an integration from this downstream point, the measurement, and then you're going to integrate. Let's do the supercritical integration. Okay, and you've got two lines here, and at some point they have to join with the hydraulic jump. Now, theoretically, this is a vertical line, but you saw it wasn't. So, how accurate do you think you're going to be? So, how do you predict when you're going to get those two joining? Well, we do for each line. So, the supercritical integration on the left here, we'll do a conjugate depth integration. And that conjugate depth integration goes along there, and where that crosses the subcritical integration is where the jump happens. Now you can do it the opposite way as well. You can do the subcritical conjugate depth line. Perhaps I should colour that in blue. Subcritical conjugate depth line, and where that crosses the supercritical is where the jump will occur. That's the prediction. That's what you're trying to do. Now you can do it twice with the two different conjugate depth lines, and they should be in the same place, but they might not be, and they also might not be in the same place as where you measured in the lab, or where the data says it is in the lab. And you need to think of the reasons why they're not the same, why the lab's not the same. And it might be to do with your accuracy of integration. It might be to do with your the interpretation of the data, or the accuracy of the data. Okay, thank you.